Hello everyone, myself Abhi, a second year student at IIT Roorkee. Today we are going to discuss an important aspect of data science, the limitation of principal component analysis or PCA. Okay, so moving forward, so before discussing the limitation of PCA, it's important to understand what PCA is. PCA is a widely used technique in data science. It's aimed to reduce the dimensionality of a dataset while retaining as much information as possible. Okay, so basically PCA is a technique in which we want to reduce the feature of our dataset, or you can say reduce the dimensionality of our dataset. And the process or technique which it uses is feature extraction, in which it's create a new set of features while retaining the maximum possible information. Okay, however, it is important to understand the limitation of PCA to avoid potential pitfalls. This presentation will explore the boundaries of PCA and discuss its limitation. Okay, so moving forward, so here we are going to discuss some PCA fundamentals. PCA is a linear transformation technique that identifies the direction, or you can say principal component along which the data varies the most. As you can see in the given figure, along the this line, along this line, you can see that our given data varies the most. So this can be one of our principal component, or you can say this is one of our principal component. Okay, because you can see along this line, our data varies the most, and this is the basic of PCA. These components are orthogonal, so there may be more than one principal component. So in this given figure, one principal component will be perpendicular to this principal component, and these components are orthogonal and capturing the maximum variance in the data by projecting the data on a lower dimension subspace defined by the principal component. So you can see that this is the subspace which we are defining using principal component. Okay, or we can effectively reduce the dimension of the data set. As you can see that initially our data set is of 2D, but after using PCA we are going to select axis which is 1D, and hence our dimension is reduced. Okay, here are the some of the limitations which we are going to discuss today. First one is linearity assumption, second orthogonal transformation, third is loss of interpretability, fourth is sensitivity to outliers, fifth one is the determining the number of components, and the last and the sixth is variance based criterion. There may be more than this limitation of PCA, but in our today's session we are going to discuss only these. So moving forward to the first assumption, that is linearity assumption. Limitation 1, linearity assumption. PC assume that the dataset is a linear combination of variables which may be true or may not be true. Okay, here variables mean the feature of the dataset. However, if the underlying relationship is non-linear, PC may fail to capture the true structure of the data. Here, as you can see in the given figure, our data spread is spherical, which means that principal axis may be any random axis. For example, if we choose this as one of our principal component, and perpendicular to this is this one. So here we get some variance. Say this one is the variance for this set, and let us choose some another set of principal component. Okay, like if we choose this as our principal component and perpendicular to this is this one, so for this we get this variance. So in the both set of principal components, we are getting approximately equal variance. So we are not sure to which set of principal component to choose, which may give us better result. Okay, so here PCA may fails, and to avoid or to overcome this limitation, we can use non-linear techniques like kernel PCA. Okay, and here is one more example where PCA maybe fails due to its linearity assumption, like the data is somehow like a beautiful structure like sinusoidal. So if we use PCA here, we get some principal component like this one. Okay, so here we are getting this as our projection. So here we are losing some important, or you can say beautiful structure of this spread, which may contain some important information about the data set. So here PC also may fail. Okay, so moving forward to our limitation second. Limitation second, orthogonal transformation. PCA enforces orthogonality and correlation among its principal component. So PCA assumes that the principal components are orthogonal, that is independent. While this can be advantageous for reducing redundancy, it may not be suitable for data where preserving correlation is essential. Okay, and in some cases, maintaining relationship or dependency between feature is crucial, and PCA orthogonality constraint can be drawback. So since principal component are by design orthogonal to each other, depending on the situation, we can get some far better basis vectors. Like in this case, this is one of our far better basis vector which summarize our data more correctly than this perpendicular principal component set. Okay, so in this sense, orthogonality is one of the limitation of PCA. Here are the some of the examples where orthogonal transformation can be a major issue. Like an example of image processing, preserving correlation between neighboring pixel may be the important for the visual details. But the assumption of this is that the principal component are orthogonal, which may not preserve the our required correlation between the neighboring pixel. Okay, so this can be a major issue. Other fields where this is a major issue are medical research or social science or etc. Okay, so moving forward to the limitation third. Limitation 3, loss of interpretability. PCA transform the original feature into new orthogonal axis known as principal components that maximizes the variance. These new components often lack a clear or intuitive interpretation in terms of original features. So since principal components are linear combination of features from the dataset, or you can say from the original dataset, but they are not easy to interpret. For example, it is difficult to tell which are the most important features in a dataset after computing principal component. So interpreting the meaning of principal component can be challenging, which can hinder the ability to explain the result. So this is one of the limitation of the PCA. Limitation 4, sensitivity to outliers. PCA can be sensitive to outliers in the data. A few extreme data points can disproportionately influence the principal component. Here in our given data set there is one outliers, and in upcoming slides we will see that how these outliers will affect our PCA results. Outliers can distort PCA results and lead to incorrect conclusion. Example, a single outlier can cause PCA to emphasize a direction that is not representative of majority of the data, and we will see that how this affect. Okay, so moving forward. So here we are given with a data set whose true distribution must look like this. Okay, this rounded figure. But we will see that how a single outlier this will affect our PCA results that conclude to some different results that may conclude to some different results. Okay. So here as you can see that PCA results varies from our true distribution, and this is due to one outlier. Okay. So initially our true distribution looks something like this. So according to this distribution, our principal component should be something like this. Okay, but due to one outlier, PCA may give us some different results in which principal components look something like this. So here as you can see that due to one outlier, our principal component deviates much. Okay, and this may be a limitation for PCA, and can be a major issue for concluding the true result from the given data set. So from avoiding this, we can use the another form of PCA, or you can say the advanced form of PCA, which is known as the robust PCA. Okay, so moving forward. So here as you can see that the in case of outliers, RPC giving us better result than PCA. Okay, because in the case of RPC we are getting some principal component like this, which will summarize our given data set more accurately than this principal component. Okay, so in the case of outliers, a single outlier, as you can see here, a single outliers deviates our principal component much. Okay, in that sense, PCA is more sensitive to the outliers. Okay, so in the case of outliers you can use robust PCA to get rid of this, or you can also use pre-processing techniques like box plot to get rid of the outliers. Okay, So moving forward, discussing about the next limitation of PCA. So now we will discuss one of the important limitation of PCA, that is determining the number of components. In many cases or in many scenarios, determining the number of principal component, or you can say optimal number of principal component, is quite challenging, and due to which our results may deviate too much. Okay, like let us take two cases. Like in case first, we are taking these two principal components for our concluding our results, and case second, let's say we are taking these four principal components for concluding our results. So there may be a chance, or there may be a probability that in case first, you may lose some important information which may give us better insights about our data set. So there may be a chance of losing information due to choosing less number of principal component. And if you go for case second, so there may be a chance that your data set may be overfitted, or your model may be overfitted, which may give us inaccurate results on our test data, but may give accurate result on our train data. But this is not our requirement. Our basically requirement is to perform well on train data as well as on test data. So choosing the wrong number of components can result in either excessive information loss or overfitting. Example, picking too few components may lead to a loss of essential data patterns, while selecting too many can result in noise. Okay, as we have discussed, that selecting less number of principal component may lead to excessive information loss or against information loss, and choosing too much principal components may lead to noise or overfitting. So moving forward, now we will discuss the limitation 6 of PCA, that is variance based criterion. So basically PCA assume that the principal component along which our data varies the most will give us the most accurate result. But this is not true always. PCA focus on maximizing the variance when selecting principal component. While this is often a good strategy, it may not be suitable for dataset where other aspects of data structure are more important. So there may be a dataset where the principal component having low variance will give us a more accurate result or more beautiful insights from the dataset with respect to the principal component having higher variance. Okay. PCA always consider the low variance components in the data as noise, which is not always true, and recommend us to throw away those components, but sometimes those components play a major role, and we will see a example where principal component having low variance will give us more beautiful insights from the dataset, or you can say more accurate insights from the dataset. Okay, so here is one of the example where choosing the maximum variance components, or you can say choosing the principal component with maximum variance, give us inaccurate results or inaccurate conclusion. Okay, as you can see in the first case, our principal component is this line. The first principal component is this line, and perpendicular to this is this line. So in first principal component where data varies the most, if we take projection of all these points with class A points and class B points, okay, the blue with class A and the red with class B, so we get same projection, or you can say approximately same projection for both the class, and we will get the maximum variance along this principal component. But choosing this principal component will give us inaccurate result, at this principal component did not differ class A from class B. So but if we choose principal component as our perpendicular component along which the data varies less, let me erase this. So if we choose this as our principal component, so as you can see that here the projection of class A will lie some here, and for class B will lie some here, what here. Okay, so as you can see that here is a clear distinction between the class A and class B, but here the data varies less as compared to the principal component in this case. So here as you can see that the principal component with low variance give us more accurate result than the principal component with higher variance. So this is one of the major drawback to the PCA, as you can see in the case second, where choosing the principal component with maximum variance give us the right to or accurate result. Okay, because if we take the projection of all these points on this principal component, then it will gives correctly between class A and class B. So here PCA give us correct results, assuming that the principal components with the mode variance give us accurate data or accurate result. Okay. Now concluding today's lecture, principal component analysis is a powerful dimensionality reduction and data visualization technique. However, it comes with its own set of limitations that we have explored in this lecture. Okay. So now I want to discuss one thing that suppose we are given with a data set and we have to check whether PCA perform well or not well on the given data set. So we can do some check to the data set and these checks are not the sufficient checks for the data set but are the necessary checks for the data set. Like we can check whether data set is linearly correlated or not. If data set is linearly correlated, then PCA will perform well. Okay. And the second, if our data set is of Gaussian form, then again PCA perform well. And if our given data set is of non-Gaussian form, then PCA may perform not so well on the given data set. Okay. And the third, maybe there should be very less empty value or NaN value in the given data set. If there are much NaN value in the data set, then this will affect our principal component, and in that case we get a principal component that is less significant to us. Okay, so to overcome this, we can fill the NaN value in the data set with some value like mean of the data set, or you can say mean of the feature, or you can say mode, or any another suitable value for the given data set. Okay. And apart from that, there is also one thing that you can check, that the given data set on the matrix of the form, let's say m cross n, then n should be greater than m, as we are reducing the dimension. Reducing the dimension means reducing the features. Okay, if we are reducing the features, this means we are reducing the n. And so n should be greater than m if we are reducing the n, because once we get suppose we get n less than m, then we are not able to solve it more correctly form. Okay, then we get the infinite solution, then we have to put some constraint on this to get a solution, but they will not be a true or say accurate solution. Okay, so to perform PCA well on the given data set, the given data set must be of the form m cross n, where n should be greater than m. Okay, so by understanding the strength and weakness of PCA and other analytical technique, we can make informed decision, extract meaningful insights from our data, and ultimately drive more effective and informed decision making. Okay. So as a data scientist, it's our responsibility to be aware of this limitation that we have discussed today, and to choose the right tools and techniques that aligns with our specific objectives. Okay, so in some case, like alternative dimensionality reduction method or data pre-processing approach may be more significant for our data set. Okay, so finally I am sharing some references from which I get some knowledge about this topic. Okay, you can go through these references if you need some more details of this topic. Okay, so here are the some of the references from which I get the knowledge of this topic, and if you want, you can go with this. Okay, so finally, thank you.